Here's the Duofuzz Distortion box, which uses a Germanium Diode type circuit design. And this actual unit I found for £2 on a car boot sale. Very lucky indeed, nobody noticed what it was. Later on I found out it was the holy grail of all distortion boxes. And the reason why is that it uses Germanium type diodes for the overload, which is about 0.3 volts where it comes in, and 0.7 volts would be for the silicon type. And because of Germanium type, you get a very unique sound. The modern type distortion boxes use a gain structure, which has normally got an integrated circuit chip and a transistor, and it works on the gain by just overloading and overloading, and you just get a fuzzy sound which is quite flat. This one is very grungy and very nice on the keyboards, very nice on the guitars. Later on another video we'll show you some examples, because we actually kept this distortion box. Anyway, here's Phil with the circuit diagram, giving you a quick explanation.
Right, here we have a foot pedal called the Shaftesbury Duofuzz, which I gather you guitarists love. So what we have here is actually a slightly incomplete circuit. It doesn't show the battery, and it doesn't show the fact that there's an automatic on-off switch when you unplug the thing. It also fails to show you that the switch on top of the box simply disconnects it. So in one position, if you press the switch, the input terminal there connects to the output terminal going to the two jack sockets, and this circuit does nothing. And in the other position, obviously, it's connected. In the negative return of the battery to there, that goes up to a break contact on the input jack, so that when you slide a mono jack in, the sleeve of the jack makes contact with that contact and also joins it to the earth connection on the jack socket, and that completes the negative circuit and powers it. So what have we got here? Well, the input is kind of straightforward. By the way, all the transistors are the same. They're all Japanese silicon, and they're all NPN. So the signal comes in, there's a DC blocking capacitor, surprise, surprise, and it is fed to the first transistor. Now there's quite a lot of circuitry around here. Basically, the base bias for the first transistor is derived from the emitter of the second transistor. This is a DC feedback path. If the transistors draw too much current, this voltage here rises and is fed back in negative feedback and reduces the current in the first transistor. We have a little bit of frequency compensation across the resistor, which is the collector load for this transistor, the first one. It feeds directly to the second transistor. The output is taken from the second's emitter, which is low impedance, and is fed to a pot. Now the pots on here are not labelled as one might expect them to be, as volume. One of them is balance, and one of them, excuse me, my age, you know, my memory is quite short, expander. This one is the so-called expander. The signal that is remnant after being attenuated in the pot, if at all, is fed to this transistor, which you might recognise from valve circuitry as being a split load phase splitter. Now if you turn this pot down, you get no signal at all, because this end is earthy. So if you turn that down there, it acts as a volume control. What it does do is increase the level that is fed to the distortion part of the circuit here, which is the two diodes, but I'll come to them. So if you keep the level low, you actually get no distortion. For some reason, and to be honest I can't explain it, they drive two transistors in antiphase and then they join their outputs at the collector. Now if that is balanced, you actually finish up with no signal at all, so it's quite obvious that these transistors are working on 1/2 cycle only. The thing is though, the bias arrangement here suggests that they're biased towards class A and they're conducting the whole time. So what you're getting here is a partial short circuit, which suggests that you always get distortion. The signal is then fed to two diodes, excuse me, which superficially you may think are in parallel, but if you look again, they are in reverse parallel. Now, being that these are germanium transistors, they start conducting at about 0.3 or 0.4 of a volt. So any signal, negative or positive, above 0.4 of a volt is clipped. So these cause severe distortion. It doesn't absolutely clip the voltage because there is a series resistance in the diode. However, it is going towards a square wave, and if you put a large signal into them, it will actually give you a pretty good square wave, and square waves sound horrid. So this control here determines how much distortion you get relative to a given level of input signal. If that changes, of course, so does the level here, regardless of the adjustment of the pot. But it determines how much of each half cycle exceeds the 400 millivolt threshold and is therefore clipped. The rest of the circuit is basically just an amplifier which amplifies the now rather attenuated signal, despite the fact we have got 5 transistors before the diodes. The diodes have seriously limited the level, whether it's distorted or not. It is then amplified here and goes out to your amplifier. There is a switch here marked tone 1 and tone 2. Well, basically all you really got here, if you follow the circuit, this one here, there is a resistor, a potential divider with a second resistor, but we've got a 0.1, so this is a bit of a muffler. The 0.1 shorts out part of the high frequency response, so that's a bit muffled. If you switch it to the other position, you just have a straightforward resistive potential divider with no tone control effects. This feeds the other pot, which again, if you turn it right down, shorts the circuit out. So really this is a volume control. But what it does do, between the two pots, if you want low distortion, you keep this one low and turn the gain up here high to compensate for the attenuation here. If you want a lot of distortion, you turn this one up full, and if the output level is excessive, you turn this one down appropriately. And that's basically it. This circuit is perfectly copyable if you wanted to build your own. You might have difficulty getting the transistors because they're old-fashioned. My guess is that pretty well any silicon NPN transistor, small signal transistor, will do. BC109 comes to mind. BC108 will probably be perfectly adequate in here. The 109 perhaps there for low noise, but then I'm not sure that people are looking for low noise in this kind of circuitry, frankly. The OA81s you can still get. Unlike germanium transistors, germanium diodes are still produced because they still have uses where silicon aren't suitable, and this will be one of them. If you were to put in there something like 1N914s or 4148s, which are silicon, I suspect it would work very much the same, but you need to turn this pot up higher to get the same amount of distortion, because the forward voltage threshold goes from 0.4 to about 0.7 volts. But as I say, you can still get germanium diodes, but they will cost more than silicon ones because they're used in very small quantities compared to the quantities of silicon diodes that are now used, signal or power. And that's about all.
If you found this tutorial very useful and would like to see more, then please subscribe to our YouTube channel, Patreon, Facebook and Twitter accounts. So far to date we have covered dozens of vintage valve amplifiers and equipment. starting with basic items such as Danset, Bush and Philips record players. We've also covered the Mullard 3.3 and the 510 valve amplifiers, the mic amp and mixer circuit based around the EF86, the Hacker and Dynatron record players, Leak TL10, quad valve amplifiers, GEC MOV division, Radford, Pi, Dynaco Stereo 70 and many other British and foreign audio circuits. We are in the process of shooting lots more videos on a regular basis, and we will be uploading often. We cover hi-fi, musicians and recording studio equipment, as well as vintage radio circuits. Please go to the website for more details.